Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you're all doing okay today. It's supposed to warm up. It is so icy out. I was coming to campus today and slid into an intersection, those panicked moments of the light's turning yellow now. And if it were ideal conditions, I would have plenty of time to stop. And the panic of just should I stop? And then not stopping soon enough, and then stopping only really halfway in the intersection with people getting mad at you because you're halfway in the intersection. It's supposed to warm up today, so I'm really hoping that on the way home it's a little bit less icy. I hope. Yeah, I hope you're all doing okay today. First things first, what I want to do before we even get into this stuff is I want to take a look at the course schedule for next week. So next week is starting to be week 4, and you might notice that this is the same as what it used to say for week 3. So what I've done here, everything after what we're doing right now, I'll scroll back up just a second. I've changed this to be weeks 2 and 3. So we've spent weeks 2 and 3 talking about file systems implementation. And then what we're going to be talking about next week is file systems consistency and redundancy. So this is to say ultimately that if you've done these readings already for this week, there are no new readings for next week. There's nothing extra for you to do for next week to prepare, but we will be starting this stuff on Monday next week. We'll be starting this stuff on Monday next week. I really just want to make sure that we're giving the appropriate amount of time to treat file systems with the attention that it needs for what I want to have in this course. So file systems consistency and redundancy has been moved to next week. Everything else after that has been increased basically by 1 week. And then at the very end here, I've pushed swapping off the end. Swapping is something that we will be able to hand wave about when we're talking about paging anyway, so it doesn't really need a whole week of time to talk about it. But I want to keep it here just so you have a sense of what was there in the first place. The other thing that I want to bring to your attention on the course webpage is this announcement that I made about TA. We have a TA in this course. His name is Khaled, and he is going to be holding office hours regularly throughout the term on top of my office hours. He's going to be in E2464. If you know where my office is, maybe that's a bad point to reference. If you know where the computer labs are on the 4th floor of E2, he's in the same hallway that the computer labs are. There's one little office that's right before the very last computer lab at the end of the hallway, and that's where Khaled's going to be sitting. He'll be there on Tuesdays and Thursdays from 1 to 3 p.m. If you need some additional support beyond the time that I'm available to you, or my times don't work for you or whatever, Khaled is a good resource to get some extra help in terms of working through your assignments and other course material. All right, so what I'd like to do today is I want to finish up with exFAT. So we got pretty close to the end last time in terms of the directory structure of exFAT. So taking a look at this root of our volume and then trying to find out stuff about how do I get 2 files from these directory entries, kind of in the same way that we did with ext2. I'd like to be able to finish up that today, and then I'm going to spend the rest of the time today talking about assignment 1. With assignment 1, I am providing you with a great deal of structure, and the structure that I'm giving you is to some extent kind of rigid. Like, you have to stick to what I'm telling you to do in terms of the way that you're expected to implement what you're implementing. And so I want to spend time talking to you about what that rigid structure is. And then I also want to spend time talking to you about how you're going to be assessed on it. So what things you should be looking for in terms of where you should be focusing your time for working on the assignment. So with that, let's finish looking at the documentation for exFAT, and let's finish talking about the overall structure of exFAT. So I've got this back up on my screen. We're pushed a little bit back from where we were last time, but that's okay because at the very end of last class, I was kind of getting to the point of a little bit of hand wavy, like there are directory entries here for this other directory. So I want to take a step back and just make sure that we can do that. What I'm going to do here is I want to spend some time talking just a little bit about the directory that we're looking at right now. So last time we started with the root directory. This first cluster of root directory here, this is metadata that we got from our main boot sector itself. This is one of the properties in the main boot sector. And this says this is the first cluster of the root directory itself. So when we get to the cluster heap, we're going to be able to interpret the contents of the cluster as directory entries. These are directory entries for a directory because this is a directory. And we know it's a directory because it's the first cluster of the root directory. This is told to us by default. When we were taking a look at the first cluster of the root directory, our first step here was to build a cluster chain for this root directory. Cluster chains are built up by taking a look at the FAT, the file allocation table itself. And so the first cluster of our root directory was entry number 2. And what that says is look at entry number 2 in the FAT and see what its value is to find the next thing in the cluster chain. So the next node in our linked list of clusters. What we eventually found by following this entry number 3 down to entry 3 here is this end of cluster chain marker. F, all F's here says there are no more nodes in this list. You can interpret this as being null in your list. This is the end of the list. There's nothing else here for this cluster chain. Once we had that information, we started taking a look at the actual cluster heap itself. So this is the cluster heap. These are the 2 clusters that we have for the root directory here. And in the example that we were doing, the very first entry here is the beginning of an entry set for the files that are in this directory. The files that are in the root directory are up here. There is a file, a plain text file that's called hello.txt, and then a directory that's called directory. It's called directory. So there's 2 things in our root directory. So we have 2 file entry sets. We have 2 entry sets in the directory entries for the clusters for this directory. The first entry set here, and all entry sets are ordered in the same way, consists of a file directory entry. The file directory entry tells us the type of the thing that this entry set refers to. So the first entry here is referring to the first file up here. And so the type that we're able to get out of this is a regular file. If we look at the entry set entry that has the first cluster for this file, and we go to that cluster, it will be the data for that file. This is like kind of like the direct block pointer that we're going to get to here. When we're looking at this file, we're going to interpret it as a file because the file directory entry has this property that says its type is file. The stream extension here tells us what the first cluster is. So like I said, this is like our direct block pointer. This says if you go to this block or this cluster, you're going to find immediately the first bytes of the file that are called hello.txt. And then what we have after that is this file name entry. The file name directory entry has the file name embedded within it. There can be more than one file name directory entry. There will always be one, at least one. There can be more than one. Each file name directory entry has up to 15 characters in it, and each file can have a file name that is 255 characters long. So there can be many file name directory entries in an entry set, but there will always be at least one. What comes after that in this cluster is the next entry set, the start of the next entry set. So each time we see a file entry, we're starting a new entry set for another file that's in the directory that we're looking at right now. This time we're looking at the entry set for the directory that's called directory up here. And the file directory entry says this is a directory. So if you follow the first cluster in the stream extension, you're going to find more directory entries. So where the file directory entry for hello.txt says this is a file, and if you follow the stream extension's first cluster, you'll find bytes of the file. This one says it's a directory. If you follow the first cluster to the cluster heap, you're going to find more directory entries, and these are the directory entries that are contained within this directory. Once we've got that stream extension that tells us where that first cluster is, the file name contains up to 15 characters of that file's name. Directory has fewer than 15 characters, so it's contained entirely within one directory entry here. The remaining 2 spots that we've got, all directory entries, remember, are exactly 32 bytes in size. They are fixed in size. They will always be exactly 32 bytes in size. The remaining space that we've got here have directory entries that have a type of 0, which says that this is the end of the directory. There are no more entries in this directory. There's only 2 files, so there's only 2 entry sets. Any empty space that we have here in that directory will have entry type 0. There are no more directory entries in this directory. So what I want to do now is I want to quickly take a look at how do I go from this directory entry to building up a cluster chain for my file? The file that I'm going to look at here is hello.txt. And then I also quickly want to look at this idea of what the directory entries are going to look like for directory itself. The goal here is that I want to be able to see how we're going from place to place in the file system, just like we were doing with the ext2, but visually. So the first thing that I want to take a look at here is going to be the getting the data for the file that's called hello.txt. I want to get the data for this file itself. So the first thing that I have to do with this is I'm going to have to build a cluster chain for this file. I must build a cluster chain for this file. I'm building this up first, but it's also possible for you to build the cluster chain as you're reading clusters. You can do it a different way if you want to. You can kind of like go to the first cluster, read the full cluster, get to the end of the cluster, then go back to find the other cluster in the cluster chain. But I'm just doing it, build the linked list first, just to kind of keep these concepts separate from each other. So I want to build a cluster chain for hello.txt. And what I'm told is that the first cluster for this file is cluster number 4. So that's the first node in my list. I'm going to look at cluster number 4 up here in my cluster heap, and the entry that's there is FFFFFFF. And that says immediately that there's only one node in this list. There's only one cluster that this file has worth of data. So my list here immediately just consists of 4 and then null. There's nothing else in my list. And if I go to cluster 4 here, I'm just going to make some stuff up. I'm going to write the words hi, new line. So this would actually be our ASCII bytes. So thinking back to hexdump and ext2, where we got, I think it was block B, looking at the contents of our README file in that file, this is what we would see as HI exclamation point backslash N, the data for the file that we've got here. This file then is 4 bytes long. The rest of the cluster is just, I don't know. It might be zeros, it might be a bunch of other stuff, but the 4 bytes that are in the file are going to be the first 4 bytes of this cluster. The rest of it is unallocated. It might be zeros, it might be other garbage that happens to be left there from the last file that may have used that cluster. Once I've got that, I want to go back to my root directory here. And now I want to start trying to spin on the directory itself, the directory that's referred to from our root directory. The first cluster of this directory is cluster number 5 here. So I need to build another cluster chain for this. And the first cluster is number 5. I'm going to look up here at cluster number, entry number 5 in my FAT. It points to number 6. So that's the next thing in my list. Entry number 6 here points at FFFFFF. So this is the end of my chain. I've got 2 nodes in this cluster chain. I've got 2 files in here. One of them is called hi.txt, and the other one is called image.jpg. And so I'm going to have 2 entry sets in this directory structure. So the clusters that I'm going to be looking at for this directory will have entry sets. I know that it's a directory because the file directory entry for this told me that it was a directory. So when I follow this to cluster number 5, I'm going to be able to interpret the contents of cluster number 5 as more directory entries. So 32-byte blocks, 32-byte structures. I'm able to read through this to find each of those things. Our entry sets always consist of the same the same sets. So the first entry here is going to be a file. It's going to tell me that the type of this thing is it's a file. So the first entry that we're looking at here is for hi.txt. That's what this one is going to be referring to. The stream extension is going to tell me that the first cluster for this file is at cluster number 7, and we're going to have a file name entry for hi.txt that fully contains hi.txt because it's fewer than 15 characters. After that, I'm going to have the directory entries for image.jpg. So that's going to start here. We're going to have a file directory entry. It's going to tell us that this is a file. And then immediately following that, in our next cluster here, we'll have a stream extension that tells me that the cluster starts, the first cluster for this is number 8. We'll have a file name. And then we'll have 2 end of directory entries. There are no more directory entries in this thing. So if I wanted to follow the cluster chain for hi.txt, I'd have to look at the stream extension here, go up to my FAT, see that the first node here is number 7. It immediately points to the end of the cluster chain marker. The contents for this would be here. It would also say, hello, exclamation point, \n. Our actual data for this file would be contained within cluster 7. All right. Is this looking okay so far? Okay. Any questions? Yeah.
Like when reading the data region there with all the zeros at the end,
yep.
I'm guessing that we somehow know when the end of the cluster is, so that way if like there are no zero entries, like it is completely filled up, we know when the end of the cluster is still.
Yeah. So that's a great question. And I'm going to try to repeat it just for recording sake. Do we know when a cluster ends so that in case there is no extra space at the end, that we know that that's the end of the directory entry set? The answer is yeah, you know what the cluster size is. You always know what the cluster size is. And because you know what the cluster size is, so this is this expression up here. This is 1 left shift bytes per sector shift times 1 left shift sectors per cluster shift. You know what that size is. You also know that all directory entries are always 32 bytes. They're never going to be anything else. They will always be 32 bytes in size. And so you can divide the cluster size by 32 to figure out how many directory entries there actually are possible in this thing. And then you can count. I've read 1, I've read 2, I've read 3, I've read 4, I've read 5, up to however many there could be in a cluster to decide when to stop reading directory entries. If you get to the point of not finding an end of directory entry, yeah.
Can you have a directory within a directory?
Can you have a directory within a directory? Yeah, absolutely. So this actually shows us a directory within a directory. The E drive is not really a named directory, it's just the root directory. So this is like / on our Mac OS and Linux systems. If I opened up Windows Explorer, it would be like the E drive. And when you open that, there's stuff inside of it. And so we can kind of say that this itself is a directory. We don't have any metadata about it. We're just told that this is the first cluster of the root directory. It's told to us that this is a directory. And then this directory here is a directory inside of that directory. So the entries that we have here in file, the third directory entry for this that refers to this directory thing itself, it says this is a directory inside of a directory. And you can have directories that are as deeply nested as basically as deep as you have clusters and cluster chains to be able to represent them. Yeah. Yeah.
Was the dot and dot omitted for simplicity?
That is an excellent question. Was the dot and dot omitted for simplicity? Dot and dot do not exist in exFAT. There are no references back to the parent. So if you look at a directory, so for example, if we started looking at this cluster here, cluster number 5, that refers to this directory, there's no way within the contents of this directory for us to know what directory it's contained within. There's no way for us to know how to go back to the parent from this. The only way for us to really go back to the parent is to go to the root directory and basically find the parent for that directory. You can keep track of this stuff, like you can keep track of the full path of where you are as you change into directories and use that information to go backwards, but there's no direct reference to the parent directory in directory entries in exFAT. This is a pretty big difference between the inode structure directory entries that we had with ext2 and what we're looking at right now with exFAT. That's a really good question. Thank you for asking that. Yeah. Why are we shifting bytes to find cluster size? So the properties on exFAT, I'm going to come back to this diagram in just a second. In the main boot region itself, and in the main boot sector here, we have these properties that are called bytes per sector shift and sectors per cluster shift. These are effectively, if I actually click on this instead of just hand waving it, it tells us that this is n, where we have an expression that's log-based to n. And if we do one left shift by that number, we're raising 2 to the power of that number. So that expression basically gives us the ability to compute the number of bytes from bytes per sector shift. So this tells us that a sector will have to the power of 8 bytes, 2 to the power of 8 bytes per sector. And if we shift 1 by that 8, we're going to get whatever the value of 2 to the 8 is. Why is it in log2n? So that we can put, basically so that we can put this value into a single byte as opposed to having to store it in 4 bytes. So you could put really big numbers in a 4-byte value, but you can also represent very big numbers in a single byte by calling it, like, if you raise 2 to the power of 16k, for example, or whatever the max value of an 8-bit value is going to be, it's going to be quite a lot bigger than what you can represent with a 4-byte value. Yeah. All right. So the very last things that I want to do here are to kind of like come back to this documentation and then like make some connections between the diagram that we've drawn with this documentation. The first thing that I actually want to do here is I want to start making connections between the main boot sector values and the values and the structure that we're looking at in this file system. So the first thing that I want to take a look at here is the FAT offset field. I'm going to go back to my diagram, and I'm actually going to come back up to this diagram right here. And what I want to do with this is I want to to give you the expression to how to get to the fat. If you're looking at this as though it were a file, excuse me. So the fat here starts at fat offset. Whoops. It starts at fat offset. And this is a value that we are getting from our main boot sector. Fat offset is a value that we're getting from our main boot sector. This is measured in sectors. Fat offset is measured in sectors. And so we can use an expression that looks like this: 1 left shift bytes per sector shift. Also in my main boot sector, to be able to get to the start of the fat. If I use this expression in an LSEQ, that will take me to the first part of the fat, the very first entries in my fat. The other entry that I want to think about here, I'm going to pop just back up to this documentation for a second, is the cluster heap offset. The cluster heap offset is also measured in sectors. So to get to the beginning of my cluster heap, which remember is cluster number 2, it is not cluster 0, it's cluster number 2. To get to the beginning of my cluster heap, which is right here, the expression that I'm going to use to get to the beginning of my cluster heap is cluster heap offset times 1 left shift bytes per sector shift. That will take me to the cluster heap itself. Once I'm at the cluster heap, then I'm going to want to start shifting around in clusters. I don't want to shift by sectors anymore. I want to shift in clusters. To get to cluster number 3, the very start of cluster number 3, the expression that I'm going to use, and as I said when I was talking about using LSEQ before, my strong preference is to do an LSEQ to get to an absolute location, like the start of the cluster heap, and then do relative offsets using that seek cur. So I'm going to seek to the start of my cluster heap, and then I'm going to seek relative to that to the cluster that I want to get to. The way that I'm going to do that is I'm going to go to the cluster number, less 2, always minus 2, always minus 2, always minus 2, because it's a 2-based array, and this is ridiculous, but this is where we're at. Cluster number minus 2 times 1 left shift, sorry about that, 1 left shift bytes per sector shift times 1 left shift bytes per cluster, sectors per cluster shift. This expression will take me to the start of a cluster in the cluster heap, once I have seeked to the beginning of the cluster heap itself. So movement to things before the cluster heap are in sectors, and we can use that 1 left shift bytes per sector shift. Movement within the cluster heap is going to be based on clusters, and it's this expression here where we're adding the number of sectors per cluster to that. I'll post this document up on the course webpage just like I did the last time, so you'll have a copy of it as a PDF. Yeah.
When we get to the heap, why are we differentiating between sector and clusters? What's the major difference between them?
So sectors, the difference between sectors and clusters is mainly so that our main boot sector can be contained within an entire sector. And also because we can't know what the cluster size is until we've read the main boot sector in the first place. So we have to be able to have some like basic unit of measurement to say this is how I'm going to find out more information about this file system. And then the rest of the stuff can just fit within sectors. It's been designed intentionally to fit within sector sizes as opposed to cluster sizes. But once we get to the cluster heap, we really want the cluster heap size to be variable in nature. So I want to be able to make clusters that are as small as the sector size. So each cluster might be exactly the same as each cluster might be the same size as a sector, but more typically each cluster is 4K or more in size. I'm not sure if that answers your question. I hope it starts to answer your question though. Variable cluster, when I say variable cluster size, I mean when we create the file system. So when I initially create the file system, I want to be able to have 4K clusters as opposed to 512 byte clusters. And I want to be able to specify that to minimize the amount of wasted space in my file system, or I want to change it based on the workload that I'm using. If I'm making lots of really, really small files, I want my cluster size to be pretty small so that I'm not wasting very much space. If many of the files that I'm creating are very, very big, I want to make my cluster size bigger so that I can reliably read bigger chunks of the file all in one go compared to having smaller cluster sizes. So if I'm putting 4 GB size files into this file system, I want my clusters to be bigger so that I can read 4 times as much data at a time. 512 fits into 4K 8 times. I want to read 8 times as much data at a time as opposed to having to read 8 times to get the same amount of data. All right. Okay, cool. So that's kind of moving around our cluster heap. What I want to do now is just really take a look at a couple of the other sections of this text. So I want to go to this section 4. This is the FAT region. This is literally describing that FAT section of our file system. And what this tells us is that the FAT itself is a zero-based array. The first entry in my FAT is number 0. It's actually number 0. But each entry in this is going to be a 4-byte entry. So at offset 0 is entry number 0. It's 4 bytes in size. Entry number 1 is at byte number 4. Entry number 2 is at byte number 8, and so on. So there's 4 byte values here that represent these numbers that we're using to build up that whole cluster chain thing. I'm going to go back up to the top, and I'm going to take a look at the cluster, the data region itself. This here is the single most important sentence of this thing to me that lots of people overlook, and it says, importantly, the first cluster of the cluster heap has index 2. This is a 2-based array of things, so we're always doing things offset by 2 here. But each of the clusters then is going to be a cluster in size. So once we're in that cluster heap, we need to start maneuvering around the file system in units of clusters. One thing that this makes reference to here is that the exFAT has an allocation bitmap. We'll look at this in a second. exFAT actually has an allocation structure where older versions of FAT did not have this allocation structure. The FAT was the allocation structure to determine whether or not a cluster was used in the data region. We're going to look at this in just a second. And we're going to look at this in just a second in the form of the directory structure that we've got. The directory structure, so once we're looking at the cluster heap, once we're looking at a cluster for a directory, it's going to be filled with these directory entries. Directory entries are all 32 bytes in size. They are always 32 bytes in size. Every directory entry is 32 bytes in size. And they're going to have a bunch of different stuff in them. I'm going to step past this for just a moment, but parts like 6.2.1 and 6.2 in general are important for us to be able to find, but we'll be able to find them again once we get down here. And I'm going to keep going down here. I'm going to keep going down. I'm going to keep going down to directory entry definitions. This is section 7. There are many different directory entry types. All of these are 32 bytes in size. They are all exactly 32 bytes in size. The ones that we care about are file, stream extension, and file name. The diagram that I've drawn for you omits a bunch of these. The allocation bitmap, the upcase table, the volume label, the volume GUID, and exFAT padding, these are directory entries that are in the root directory. They are there before any entry sets for the files, and the allocation bitmap and the volume label specifically are file system metadata. The allocation bitmap is referring to where the allocation structure is for the file system, and the allocation structure is stored in the cluster heap. It's stored in the cluster heap as though it's regular data for the file system. The volume label is stored in a directory entry for the root directory, where it's stored in the superblock for things like VSFS and ext2. I don't have a good answer for why these things are kept in the directory for the root directory. I don't know, but I think it's related to this whole idea of backwards compatibility with older versions of the FAT file system. The last thing that I want to do here is I'm going to take a look at the stream extension one. The stream extension entry table here kind of describes a lot of the same things that we're going to see in the other entry types. The very first byte of every type of directory entry is the entry type. It's always going to be 1 byte represents what kind of directory entry this is. So the first byte that you read from a directory entry will say, this is file name, this is stream extension, this is something else. This is the byte that you need to refer to decide what kind of directory entry this thing is. The stream extension itself has things like the first cluster field. And I'm going to go back up to where we had the file entry here. The file entry here has file attributes. And this tells us things like read only, but importantly, whether or not it's a directory. This is a bit. This is one single bit in this thing, so you'll have to do a little bit of reminding yourself about bit masking, so using like ampersand to mask bits off. My approach to this is really just to use hard-coded values for what that 1 bit on actually is, and then use my ampersand to test with that. All right, okay. What I want to do right now is I want to spend a little bit of time taking a look at our assignment, but I'm also going to promise that I'm going to put time in the next 2 Fridays for questions in class about the assignment. I'm going to make sure that there's time to ask questions about it. I'm going to pop over here to the content section for assignments, and I've put 3 things in this section. One is the description itself, and then 2 links to things on GitLab. I'm going to open up the assignment description first. What I'm asking you to do is implement something that looks like the POSIX API. So you're going to be implementing functions that are mount, which is kind of like, I want you to read the main boot sector and do some checking on the metadata for the main boot sector. I want you to write a function called open, which is going to take a path, and you're going to have to find that file in the file system and then return a file descriptor. I want you to write a function that's called read, where you're actually going to be like building cluster chains and getting data for the file from the file system. And then a function that's called getDents, get directory entries. So this is going to be a function that's going to take the structure that is exFAT and transform it into something that is defined by this interface so that we can do stuff like listing the contents of directories. I have pre-changed the due date for this assignment from Friday, February 7th to Wednesday, February 12th. So there's an extra number of days that have been attached to the due date of this from what was originally posted in the course syllabus. you're more than welcome to hand it in the originally stated due date if you want to, but the due date is what's posted here for the assignment. I'll point at this and I'll say that you got to have this run on Aviary. It must compile and run on Aviary. This is the environment that the graders are going to be using to assess your work. Your work must compile and run on Aviary. In terms of like things that fail, if your code seg faults or if you get a bus error, what's going to happen is that the part that that grader is currently assessing will be reduced in the overall value that you can get. You're not going to get 0, but you're not going to be able to earn full points on that thing. The other part is that if your code doesn't compile, we're not going to assess it at all. It must compile on Aviary. Having something compile on Aviary at this point should be achievable for everybody in the course. So just make sure your code compiles before you submit it. I'm going to skip past a lot of this stuff because I'm going to tell you about it by taking a look at the GitLab projects. So there's 2 projects that I've linked to on GitLab. These are in the course webpage, and they're also linked to in this document. The first one is the template here. I would strongly recommend that you just clone this repository. And I'm going to show you how to do that right now so that if you've never used Git before, you can get started with this. If you go to this link, you can copy this URL and you can go to your terminal. You can run git clone and then paste this into your terminal, and it will now be on your system. So if we've cloned this stuff, I'm actually going to take a look at this in my repository here. There's a README file. I'm not going to open the README file because I'm going to tell you what the README file says verbally right now. The thing that I do want to take a look at here right now is nqpio.h. This is the interface that you must implement. You're not permitted to change this file at all. You must implement this interface because the code that we're going to be using to test your implementation will use this interface for the assessment. I'm going to scroll past these structures, and I'm going to go to the actual function definitions here. So nqp mount is one where you are going to be passed a file name, and the file name is, this is the volume. This is the name of the file that contains the volume that I'm going to be reading. Your implementation is going to need to do some basic checking on the file system to make sure that it is valid, like checking the boot signature, for example, or checking that must be 0 fields is actually all zeros, or checking that the file system type is exFAT space, space, space. And then it's going to return either an error that says, nah, this is not a valid file system, or it's going to say, okay, this is a valid file system. This is a function that must be called before the other functions can be called. We're not expecting read to work without having mounted a file system in the first place. So this is something that when you write it is going to be like a static variable that refers to the file system that you have started to work with. Unmount is kind of like close. It's going to like take that file system and just shut it down. So anything that you have done, we're not doing any write support, so you don't need to worry about changing anything on the disk. You just need to like disconnect from that file. The open function and the close function, open will take a path inside the volume. It will take a path that's inside the volume starting at the root directory. What it's going to do is try to find that file. If it's able to find the file by looking at the directory entries, or the directory by looking at the directory entries, then it will create an entry in an open file table, and you will return the file descriptor. So this is the index into that open file table. Close is going to take a file descriptor and remove it from the open file, either get data for a file or get directory entries for a directory. The directory entries for the getDents function are defined up in this file. The directory entry structure that you should be returning is this directory entry structure. There are no inodes in exFAT, so this inode number should be the first cluster number. That's effectively what you're going to be doing for these directory entries. The name and type are straightforward. The name is the name of the file that you're looking at, and the type is going to be either a directory or a regular file. For what I'm asking you to do, I would suggest that you stage this implementation. Mount is the first thing that you're going to want to do because everything relies on mount working correctly. You don't actually need to implement an open file table first. You can work on this from the perspective of there will only ever be one open file, and then proceed with implementing all of the stuff for that, and then afterwards change that to be you could have multiple open files. But I would suggest that you just start with the assumption that there will be exactly one open file to get things working and then move on to other stuff after that. The other file that's in this directory that I want to bring to your attention is this nqp exFAT types.h. You are permitted to change this file. You don't have to use this file at all if you don't want to, but it's painful to have to type all this stuff in. So I've done it for you, so you don't have to if you don't want to. I would strongly recommend that you use this, but you do not actually need to use this if you don't want to. The main boot record is the main boot record. This is all the metadata that's in the main boot record, and I've set it up such that you can read the whole thing all in one go, as opposed to reading each of these things individually. What's beneath this is all of the directory entry types. Again, you don't need to use this, but I've typed it all in for you. You are welcome to use it if you want. You are welcome to change this file if you want, but you don't have to use this if you don't want to. So we have the file directory entry, we have a stream extension, we have a file name, allocation, bitmap, volume label, and then what I have here, this is the one that I would suggest that you work with, is the directory entry structure. It has one byte that is the entry type, and then a union of the other kinds of directory entries. If you're thinking back to 2160 here, union means that this space will be the size of the largest type in the union. So all of these are 31 bytes. All of them are 31 bytes. So this entire structure is 32 bytes in total. When you read this in, you can read into a directory entry, look at the entry type, and then test to see if it is, for example, 0x85 here. Then you can read the file property from this union, and you have a fully constructed file thing. If you read 32 bytes into this thing, it is a file type. You can use the file property of that union just to get the information that you need from the file type itself. There's also this entry set struct that you are welcome to use if you want to. You don't have to. When I was doing it, this was my mental model. I want to build up these entry sets first, and then I'm going to work with them that way. The other thing I want to show you is, well, this at the end here, which is these are just all the directory entry types that are listed in the documentation for exFAT. You can figure out these hex codes by looking at all of the entries and their documentation, and it tells you what bit should be where. But again, I've done it for you, so you can just use these values if you want to. There are other kinds of directory entries other than what we see here. And if you find other kinds of directory entries, you can safely just ignore them. Move to the next 32 bytes in the file. The other thing that I want to show here, the very last thing, is I've got nqp exFAT.c. This is just an empty file that has nothing in it other than this Unicode to ASCII function. Unicode to ASCII is a function that I've written that takes the values from file name types. Remember that these are 16-bit characters. This just converts it to ASCII array for you so that it's a lot easier to print out with something like printf. And then the rest of these are just empty implementations of those functions, just to get you started with this stuff. You should modify this file. The last thing here is cat.c, and this is an example of code that would use this interface. So cat behaves the same way as cat on the command line. It will read a file and just print it to standard output. That's the only thing that this is going to do. I'm going to provide you with at least one more example program that's ls that will print out directory entries, but I'll be providing that to you next week sometime. The other thing I'll point at is the other project that's here that is volumes. This is a set of 7 different sample volumes that you can use to work with your implementation. The very first one here, empty.image, is an empty file system. It's basically the superblock or the main boot sector and then nothing else. There are directory entries for the root directory, but there are no files. So there's those metadata directory entries and nothing else. One file has a single file in the root directory and nothing else. So there's no directories. It's just directory entries that are metadata plus the directory entry set for a single file that's called readme.md, and that fits within one single cluster. One big file is a picture. It's big in quotes. It's a couple hundred K, but it spans across many clusters as opposed to being just within one single cluster. This has a property that you may not actually be able to build a cluster chain for this, and I've linked to this section 6.3.4 here that describes this no fat chain field. No fat chain says you don't actually build a cluster for this, a cluster chain for this. You just start reading contiguous clusters, starting at that first cluster up to the size of the file. Many small files is many small files. These are all just single integer file names with single integers inside of them. They're all smaller than 4 bytes. They all fit within a single cluster. Fragmented is going to be a bunch of small files where half of them got deleted, and then one big file is put on the file system to force fragmentation to happen. And then finally, nested directories and normal here are more like regular kinds of file systems that you might expect to see. I'll leave questions again for this next Friday, leave time for questions on next Friday and on the Friday after that. But what I would like to finish with is this. I hope that you all have a good weekend. If you have any questions about the assignment, please post on the course forum. Please visit me during my office hours. Please visit Khaled during his office hours. I hope you have a great weekend. I'll see you.